So welcome back to the second talk this afternoon. It's a great pleasure to have Perla Sousi, who's talking today from Cambridge on the four-dimensional uniform spanning tree.
Okay. Oops. So thanks a lot for the invitation. I'm very happy to be speaking here. So today I'm going to talk about joint work with Tom Hutchcroft, where we studied the geometry of the four-dimensional uniform spanning tree. So I'm going to start by just defining what is the uniform spanning tree for a finite graph, which probably most of you already know, but I just want to set up some notation. And then I'm going to define what we mean by a uniform spanning tree or uniform spanning forest of an infinite graph. And then I'll talk about our results. And in the last part of the talk, I'm going to explain some of the ideas behind the proofs. So, of course, everybody knows what is a tree. Now, if we have a finite graph G, then a spanning tree of G is simply a subgraph of G, which is a tree, and it spans the graph. So the vertex set of the spanning tree is the vertex set V. So if we have a finite connected graph G, then we can count all of the spanning trees of G. So I denote this by calligraphic T. This is a finite collection. And as probabilities, we like to pick things at random. So we pick a tree T uniformly at random from this calligraphic T. And we give all trees equal probability of being picked. And this is what we call the uniform spanning tree. And I will abbreviate it as UST. So in this picture here, you see a portion of the uniform spanning tree of Z2. I haven't yet defined what we mean by uniform spanning tree of an infinite graph, but one way to think of it is as a uniform spanning tree of the box that, that you see in this picture. So you may be surprised to hear, but the study of spanning trees goes back to the work of Kirkhof in 1847. So this is an 8-page long paper that he wrote, which is in German. And this is the paper where he developed a set of rules that formalize that energy and current are conserved in electrical networks. And it was in this work that the connection between uniform spanning trees and electrical networks was first established. So what he proved is that the effective resistance of an edge is equal to the ratio of the number of spanning trees that contain the edge divided by the total number of spanning trees, which is equal to the probability that the edge E belongs to a spanning tree picked at random. And he also proved in this in the same paper, he also proved the so-called matrix tree theorem, which counts the number of spanning trees of a graph in terms of the Laplacian of the graph. So everybody knows Kirkhof from his foundational work on electrical networks, and so his motivation was clearly not probabilistic, but his insight has been fruitful in both directions. And electrical networks are an important tool in order to understand the geometry of large uniform spanning trees. So I already defined what we mean by what is a uniform spanning tree of a finite graph. Now, the first question one might want to ask is, why are we interested in studying uniform spanning trees? So first of all, picking a uniform spanning tree is an essential component in many randomized algorithms in computer science. It's connected to models in statistical physics like the random cluster model. As I already mentioned, there are a lot of connections between uniform spanning trees, electrical networks, and as we'll see later in the talk, also with random walks. And Oded Schramm was actually studying the scaling limit of the uniform spanning tree, and this is what led him to develop his theory of stochastic Levner evolutions, or now called Schramm-Levner evolutions, that are either the proven or the conjectural scaling limits of conformal invariant processes on the plane. So this is a simulation due to Russell ions. So here we have a uniform spanning tree of the box, and then it's traced by the Peano curve. And the different colors that you see are the different times at which the Peano curve traces the different parts of the tree. And in the limit, this converges to what is known as an SLE8 curve. Okay, so now that I defined what is a uniform spanning tree of a finite graph, the first question we might want to ask is, how do we sample such an object? So there are several algorithms. The first one goes back to the work of Kirkhof using the matrix tree theorem, which counts the number of spanning trees. The second one is an algorithm due to David Wilson, which uses loop-erased random walks. And I'm going to talk about this now. And there is another algorithm due to Aldous and Broder, and they both acknowledge discussions with Percy Diaconis. And I'm also going to talk about this algorithm later because this is also used in our proofs. So let me start with Wilson's algorithm. And in order to define it, first, in order to explain how it works, first I have to define what we mean by the loop-erased random walk. And first, let me explain what we mean by the loop erasure of a finite path. So if gamma is a finite path of vertices in the graph G, then in order to define the loop erasure, we're going to remove loops from gamma in the chronological order in which they appear. So let me just draw here. Let's suppose this is our path gamma. Then we erase the loops in the order in which they're created. So we'll get rid of this loop first, and this one was created, and this one. And so eventually we're going to get this as the loop erasure. Okay, so this is how we can loop erase a finite path. Now, if we have a finite random walk path, then we can loop erase it. Now, if we have an infinite random walk path, which is transient, then it's clear how to define the loop erasure again, because it's going to visit every vertex only a finite number of times. So there is going to be a last time for every vertex at which it is visited. And so this is well defined. If the walk is recurrent, I'm not going to be interested in this for the talk. I will be talking about higher dimensions, but there is a way to make sense of the loop erasure by running the walk up until it reaches distance n, and then loop erasing, and then letting n go to infinity. And then if you rescale space, this is going to converge to what is known as an SLE2 curve, and it's this red curve that you see. So now I defined what we mean by the loop erasure of a finite path. So now I can talk about Wilson's algorithm. So how does it work? We start with a finite graph, and I'm going to distinguish a root vertex R, and it's arbitrary which one we pick, but we just fix it at the beginning. And then I'm going to order the remaining vertices in this way. So V1 up to Vn minus 1. So we just assign an ordering, an arbitrary one, but we just stick with it. And now, how does the algorithm work? We start a simple random walk from the first vertex in the ordering, V1, and we run it up until it hits the root R. And then we loop erase the path that we got. And then we start a random walk from the next vertex, V2. We run it until it hits the first path, and we erase loops, and we add this path to our collection. So let's say this is R here, this is V1. We start a random walk until it hits R, and then we just take its loop erasure. And then we start with V2, and then we run it up until it hits the path that we have already created, and so on, and we erase loops, and we keep going. Of course, if V2 is on the path, then it immediately hits it, so we do nothing. Okay, so it's clear that in the end, we are going to get a spanning tree, because obviously we haven't created any cycles. What is not clear is that it has the correct distribution. And this is a remarkable theorem due to David Wilson, that the tree that we obtain using this construction has actually the correct distribution. And moreover, it is independent of the root vertex that we picked and the ordering of the graph. So now how can we generalize this to an infinite graph? If we have a recurrent graph, let's say that we want to generate a uniform spanning tree of Z2, then we can use exactly the same procedure. We take 0, let's say, as the root vertex, we order the rest, and then we start a simple random walk from the first vertex that hasn't been used so far until it hits the previous path, and we keep going. And this is well defined because the random walk here is recurrent, so it will definitely hit what we have already created. And so this is going to produce a spanning tree. Now, this is the picture that I showed you earlier. Now, the reason why we call this the uniform spanning tree is because if you look at a large box around the origin, then the probability that then the tree restricted to this box will look very similar to how the uniform spanning tree of the box would look. So this is the natural measure on infinite spanning trees of Z2. So this is clear how to do it for a recurrent graph. Now, if we have a transient graph, then of course this procedure is not going to work because we'll not hit the previous parts that we have constructed. But we can just take a finite exhaustion of our graph. So let's just take these boxes, minus n to the d, and we know how to construct the uniform spanning tree measure on these boxes because here we have just a finite graph. So we call mu n the uniform spanning tree measure on Gn. And then it's not hard to show using electrical network theory that this sequence mu n is going to converge to a limiting measure mu. And again, using electrical network theory, one also can show that the limiting measure mu is independent of the exhaustion that we used. And by construction, mu is supported on graphs that contain no cycles. So mu is a forest, mu is a measure on forest on ZD, and we call this the uniform spanning forest measure on ZD. So now that we have constructed the uniform spanning forest measure on ZD, the first question we want to ask is whether it is actually a tree and whether there is a phase transition. So this was answered by Robin P. Mantle in '91, who showed that in dimensions 4 and lower, the uniform spanning forest is a single tree with probability 1, and it consists of infinitely many trees when d is greater than or equal to 5. So we see here that 4 is the critical dimension in the sense that above it, that we have a phase transition at in dimension 4. So I explained in the previous slide how to generate the uniform spanning tree of Z2 using Wilson's algorithm. So in a later paper by Benjamini, Lyons, Burns, and Schramm in 2001, they generalized Wilson's algorithm to infinite transient graphs, and they call this method Wilson's method rooted at infinity. So the difference to how Wilson's method works for recurrent graph is that instead of starting with a root vertex at time 0, we start with the empty forest. And then we start a simple random walk from the first vertex of the ordering. And we run it either forever or until it hits the previous path that we have created. And we keep doing this until we exhaust all of the vertices. So this indeed gives the correct distribution. And so from this construction, which came later than P. Mantle's result, one sees that whether the uniform spanning forest is connected or not, it boils down to the question of whether a simple random walk and an independent loop erased random walk intersect or not. So because it's harder to think about loop erased walks, let's think of two independent simple random walks. So what is the probability that two independent simple random walks intersect infinitely many times or not in ZD? So if one just uses the local central limit theorem, it's very easy to show that the expected number of intersections in dimension D, in dimension 4, grows to infinity. So by time n, the two walks have log n intersection, while in high dimensions, the expected number of intersections is finite. So this is related to the fact that the tree is connected in dimension 4, but is connected for higher dimensions. And this phase transition for the number of intersections is related to the phase transition for the number of collisions in dimension d minus 2. So dimension 2 is critical for the question of recurrence, and dimension 4 is critical for the number of intersections. And actually, the two sums that we get for the number of intersections in dimension d are the same as the number of collisions in dimension d minus 2. So, okay, so now, so I'm going to come back to the criticality of dimension 4 when I talk about our results. So now that we know that in dimension 4 in particular, we have a connected tree, the next question we want to ask is, we want to understand better the geometry of every tree of the uniform spanning forest. So now I'm going to talk about the notion of one-endedness. So we say that an infinite tree is k-ended if, starting from every vertex of the tree, there exist exactly k distinct infinite simple paths starting from this vertex. So I say distinct, I'm not saying disjoint. So you can have a picture like this. So in this case, you have two infinite rays. So this is, or maybe if also this one continues, you have three infinite rays. But we say that an infinite tree is k-ended if you have exactly k distinct infinite simple paths starting from every vertex. So clearly Z is two-ended, while the natural numbers is a one-ended tree. And so now we want to ask whether the trees of the USF are one-ended or not. And this was answered both by P. Mantle and by the later paper BLPS in 2001. So P. Mantle showed that all trees in the USF are one-ended for all d less than or equal to 4, and at most two-ended in high dimensions. And BLPS completed the picture for all dimensions d. So now we know that every tree in the uniform spanning forest is one-ended with probability 1. Okay, so now we want to quantify this one-endedness. And in order to do this, I'm going to define what we mean by the past of a vertex. So now I'm just going to pick 0 to be my vertex. So what do we mean by the past of 0? So we know that the tree containing 0 is one-ended. So you could have some finite components hanging off this infinite spine, and this continues to infinity here, and this part over here is a finite path. So let me put 0 here, and here we also have some finite pieces. So actually, let me put 0 further down. Okay, so now what is the past of 0? So this is the infinite ray. Now the past of 0 is what we obtain if we delete 0 from the tree. And so we're going to get this path. So if we delete 0, then we're going to get the infinite ray, and we're also going to get a finite piece. So the past of 0 is exactly this finite piece. And sorry, past of 0. Okay, so is the definition of the past clear? It's the part of the tree that we obtain when we delete 0 from the tree, and because the tree is one-ended, there is a unique ray to infinity, and so we just consider the finite piece that we are left with. Okay, so now we want to understand, in order to quantify this one-endedness, we want to understand how large the past of 0 is. And Tom, in his earlier work, he studied higher dimensions, d greater than or equal to 5, and he proved that the probability that the past of 0 contains a path of length n is up to constants 1 over n. So this symbol here means that we have universal constants C1 and C2, so that this probability is upper bounded by C1 times 1 over n and lower bounded by C2 times 1 over n. So whenever I write this symbol, I mean that the constants are universal for all n. The second statement is that, so the first one is for the intrinsic radius of the past. The second one is that the extrinsic radius is larger than n with probability which is 1 over n squared. And the last one is the probability that the past of 0 has size at least n grows like 1 over root n. So what this theorem shows is that higher dimensions behave in a mean field way. So these exponents here, so the exponents of n do not depend on dimension. And actually Tom proved it. Are there any questions? Yeah, sure. The constants could, yeah, I'm not 100% sure, but yeah, I think the constants must depend on dimension. But the important thing is that they do not depend on n. So yeah, so I was saying that higher dimensions behave in a mean field way, and actually Tom proved a more general universality statement. So not only for ZD, but also for transitive graphs of quintic volume growth at least, and for other classes of graphs that you have exactly the same exponents. Now the question is what happens in dimension 4, which, as I said before, is the critical dimension for this model. So when I say critical, what one expects is that in dimensions above the critical dimension, the exponents behave in a mean field way. Then in dimensions below the critical, then you have dependence on dimension. And then in the critical dimension, one expects to have logarithmic corrections to the mean field scaling. And this is what we established. We established the exponents of the logarithmic corrections. So here is our result. So what we showed is that for the extrinsic radius, the correction is log n to a third. For the extrinsic, we showed that the correction is log n to the 2/3 plus a little of 1. So what I mean by the little of 1 is that for every epsilon positive, there exists a constant c epsilon, so that this probability is upper bounded by c epsilon times log n to the 2/3 plus epsilon divided by n squared. But for the lower bound, we don't need the little of 1. So for the lower bound, and actually the lower bound, both for the first and the second statements, they are the very easy directions of the theorem. All of the work goes into proving the upper bounds. And finally, for the tail probability for the volume, we showed that it's asymptotic to log n to a 6th divided by square root n. So what I want to do in the remainder of the talk, I'm going to explain how we prove this theorem. So I'm only going to focus on the first statement, and I'm only going to prove the lower bound, which is the easy direction, but I'm going to explain what one has to do extra in order to get the upper bound. Before I start talking about the proof, I just want to say that we use the same approach as Tom used in his previous paper, which is his generalization of the Aldous-Broder algorithm for infinite graphs, and I'm going to talk about it now. And I'm going to explain where these exponents came from, because these come from the non-intersection exponents that Lawler obtained. So for the probability that a loop erased random walk does not intersect an independent simply random walk in 4 dimensions. So I'm going to explain exactly how we get these exponents. You will see it from the lower bound, and then I'll just give a very quick overview of the upper bound. Okay, so are there any questions, or shall I move to the proof ideas? Okay, so as I said, we used the generalization of the Aldous-Broder algorithm, which was developed by Tom, So first, let me explain how the Aldous-Broder algorithm works. So we start with a finite graph here. And I'm going to distinguish a vertex O, which is this red vertex here in the center. And now we start a simple random walk from the center, and we run it up until the cover time, which is the first time that the walk has visited every vertex at least once. Now, for every vertex that the walk visits, we're going to keep the edge that was used the first time that the walk visited the vertex. So let me show you. So we started from the center. Next, we went down here. It was the first time, so I painted it green. We went up, green again. We went down, nothing happened. We went there for the first time, down, nothing happened. Went to the center, we do nothing for the center. Now we went up, because this was visited before, we don't include this edge. And now at this point, we have visited everything at least once. So now we stop, that's the cover time. And now we consider the collection of the green edges that we constructed. And this, of course, is a spanning tree, because by construction, we didn't create any cycles. Now, what Aldous and Broder proved in discussions with Persidiakonis is that it has the correct distribution, which is that of the uniform spanning tree. And actually, the proof is only 2 pages long. And what they prove, so first they define a Markov chain on the space of rooted trees. So this Markov chain was considered previously by Persidiakonis. So you have a Markov chain on the space of vertices times trees. So the vertex is the root of the tree. And then you define this Markov chain, how you change, how you move from one rooted tree to another one using a random walk. And then the uniform spanning tree measure is the invariant measure for the tree component of this Markov chain. And then they show that the distribution of the tree that you get using Aldous-Broder, using this algorithm, is the same as the invariant measure of this Markov chain. So it has to be the uniform distribution. This is an argument of like 2 pages long. So now it's clear how you can generalize this algorithm to an infinite recurring graph, because you just run the walk forever. It will visit everything with probability 1, and then you apply this procedure. What is not clear is how to generalize it to an infinite transient graph. And this is what Tom did. So Tom's idea was that, so here, if we run one walk like we do for the Aldous-Broder algorithm, this doesn't work, because you cannot run it forever and expect it to visit everything, because you have a transient graph. So instead of working with just one walk, his idea was to replace the single walk by a Poissonian cloud of independent random walks. So this is the random interlacements process, which was introduced by Snitman in 2000. In order to understand the trace left by a random walk on transient graphs. So what is the random interlacements process? This is, as I said before, it's a Poisson process of bi-infinite random walk trajectories that arrive in time. So it's a Poisson process on the space of paths in the graph times time. And so in order to define a Poisson process, one has to specify the intensity measure. So I'm not going to do this because this would take some time, but I'm just going to state the important property of random interlacements that we're going to use, which is that if we fix a set, so let me fix a set K here, a finite set K in ZE, and we have this random interlacements process arriving in time. So we have these random walk trajectories. Now, what is the probability that the set K has not been hit in the time interval 0t? This is given by e to the minus t, the capacity of K. I will explain what is the capacity of K in a second. So this is the important property of random interlacements that we're going to use, which gives us the probability that the set K has not been hit in the interval 0t. So what is the capacity of K? The capacity of K is defined as the sum over all points in K of the probability starting from X that we escape K forever. And we define the capacity of K for any finite set K. So if you're familiar with the continuum analog, the Newtonian capacity, which is defined as 1 over the capacity of A is, so the capacity is the inverse of the infimum, where here we take the infimum over all probability measures mu that are supported on the set A of the integral of the green kernel of Brownian motion against the measure mu. So here we are in transient dimensions, so this is well defined. So this is the continuum analog, and the capacity that I defined here is the discrete analog of the capacity defined for any compact set of RD. And one can also prove that the capacity of K for a discrete set is also has this variational characterization where G now is the green kernel of random walk, which is the expected number of visits to Y starting from X. And we take the walk up to infinity because it's a transient walk, so this is a finite number. Okay, so this is the main property that we're going to use. So I haven't explained yet how Tom generalized this algorithm. I just defined the random interlacements process just by writing this probability. So now, how do we generalize the Aldous-Broder algorithm? So the way we do it is let's take T in R and a point X in ZT. Now I'm going to define sigma T of X to be the first time S after T, so that X is hit by a trajectory of random interlacements at time S. So sigma T of X is the first time, so for Aldous-Broder, for a finite graph, for every vertex, we're looking at the first time that the vertex was visited by the random walk, and we're taking the entrance edge. So now, for every vertex, I'm just going to look at the first time that is hit by a random walk trajectory. And this is my sigma T of X. Now, Et of X is going to be the edge traversed at time sigma T of X. So let me just erase that. So let's suppose X is here, then this edge was visited. This is the edge that was traversed. And let's say this is the first time that X is hit by a trajectory. So this is my edge Et of X. So something I didn't mention before. So with what I'm describing here, I'm not going to generate just one uniform spanning forest, but this algorithm generates a whole collection of uniform spanning forests, which is actually a Markov process of uniform spanning forest. So for every T, I'm going to define a uniform spanning forest that I will denote FT. So this is the edge that was traversed, and I'm going to keep this edge. So now I'm going to define FT to be the collection of all of these edges, and I'm going to take the opposite direction of the direction that was traversed, and I will explain in a second why I want to do that, for all X in ZT. So this gives me now an oriented spanning forest. So the reason I want to take the reverse edge is because I want to give another definition of the past. So I already said that every tree in the uniform spanning forest is one-ended. So, which means that there is a unique infinite trace starting from every vertex. So this means that we can assign directions to the edges in such a way that every edge has a unique oriented edge coming out of it. So now, if I reverse the direction of the edge et of x, we get exactly the same property that every vertex has a unique directed edge emanating from the vertex. And if we have a uniform spanning forest and by one-endedness, we can assign directions in the way I said, then we obtain what is called the oriented uniform spanning forest. And in a minute, I'm going to define the past in terms of these orientations. So now I want to state Tom's theorem. Hutchcroft. Okay, so what he showed is that Ft has a distribution of a USF for all t. So let me say that the main ingenuity here was to use the random interlacements process. Once you do this, then the proof of this theorem is quite straightforward, because another way of thinking of random interlacements is if you take a finite exhaustion of the graph and you glue everything to the outside into a boundary point, then another way of defining random interlacements is by considering a Poisson process of random walk excursions from the boundary, back to the boundary. And if one chooses the intensity of this Poisson process of excursions correctly, then as this exhaustion tends to the whole ZD, this converges to the random interlacements process on the whole of ZD. So now how can we use this to show that Ft has the correct distribution? Well, for the finite graph here, we know that running these excursions and using Aldous-Broder, we get the correct distribution. That's the Aldous-Broder theorem. And so then by taking limits, we're going to get the correct distribution in the infinite setting. So that's essentially the proof. Okay, so now once we have assigned orientations, I'm going to define the future of x in Ft to be the set of vertices V, so that there is a directed path from x to V. And I'm going to define the past of x in Ft to be V that have x in their future, so that there is a directed path from V to x. So this is the future and the past. So I defined the past previously as the finite component that we get, but because of the one-endedness and the way we assign orientations, these two definitions coincide. So if I draw here, let's say this is x, then the past of x are these vertices, and this is the future. This here is the past, is a set of vertices that point towards x. Okay, so this is how we generalize the Aldous-Broder algorithm. So in the finite setting, for every vertex, we're looking at the first time that this vertex was visited by the walk, and we're taking the edge that was used when visiting the vertex for the first time. Now, in the infinite transient setting, we look at the first time that x is hit by infinite random walk trajectory, and we take the edge that was used when x was visited. And we consider all of this collection of edges, and this gives us a realization of the uniform spanning forest. And this is a dynamical way of constructing the uniform spanning forest. And it turns out to be extremely useful in studying tail probabilities like the ones that we want to understand. And Tom has used it in other papers where he established other properties of uniform spanning forests. Okay. So let me see what the time is. Okay, so I'm going to go through the proof on the slides. So I want to explain the lower bound on the probability. So let me just move here because otherwise I will lose it. So what I want to prove is the lower bound. So what is the probability that the past of 0 contains a path of length n, and want to show that this is at least log n to a third divided by n. As I said before, this is the easy direction of the theorem, and I'm actually going to present an almost complete proof here. So in order to prove this lower bound, it's just enough to devise a strategy that gives a long path in the past. Okay, so how are we going to do this? So the first event that I'm going to consider is that, so I take some epsilon, we're going to choose the value of epsilon later. So I want 0 to be hit by a unique trajectory that I call W of the random interlacements process in the interval 0 epsilon. So let me just draw it here. So let's say that this is 0. So, okay, maybe actually let me put it here so there is something to do. Okay, so now this trajectory arrived in this direction. So this is the negative part of W, and this is the positive part of W. So now I'm going to apply the Aldous-Broder algorithm to the positive part. So what does this mean, apply the Aldous-Broder algorithm? It means that we trace this. We stop here because this vertex was already visited. And so we just apply, we just apply this procedure. And then we obtain this. So if we apply the Aldous-Broder algorithm to this positive part, then we obtain what I drew here in green. And it's not hard to show that there is going to be an infinite path that I'm going to call eta. So eta is going to be this orange path here. And eta has the distribution of a loop-erased random walk in Z4. So this is not obvious, but it's not hard to see. So I haven't, let me now quickly recall how the Aldous-Broder algorithm works. So we have that 0 is hit by this trajectory. It's the only trajectory that hits 0 in 0 epsilon. And so since we reverse directions, this here is going to perhaps contribute to the past, maybe not. But this is what I'm going to ask. And here we have the future of 0 because we reverse the direction. So now what is my strategy going to be? I'm going to take the first n steps of eta 0n, and I want these first steps of eta to survive the arrival of the other trajectories. So I want this to be in the past of 0. So first of all, since this trajectory here had priority, I don't want this trajectory to intersect this part, because if it did, then by definition, by the construction, this would cut this path, would disconnect it. So this would no longer be in the past. So I consider this event, but the negative part of W, first of all, it does not intersect this path. Now, this is, so eta, I said, is a loop-erased random walk in Z4. W is an independent simple random walk. And so the probability that they do not intersect is up to constants log n to the minus a third. And this is what Lawler proved in the 90s. So I definitely want the negative part of W to avoid this path here, but also I don't want any other trajectory to hit 0n in the interval 0 epsilon, because if it did and it came earlier, then it would get priority, so it would disconnect it. Okay, so what we see is that if A and B and C hold, then they imply the event that we want. Okay, so now we lose the picture. So the probability that we are interested in, that the path of 0 has a path of length n, is at least the probability of the intersection. And now, what is the probability of A? It's epsilon, so it's a Poisson process. So what's the probability that we have one trajectory in this interval is epsilon times e to the minus epsilon, the capacity of 0, but let's forget about this because we have something bigger here, in the smaller actually, bigger in the exponent. So I'm just going to take the probability of A to be epsilon, then the probability of B is 1 over log n to a third. And now for C, I don't want any other trajectory to hit eta 0n. And so using the important property of random interlacements that I stated earlier, the probability that conditional on eta 0n, the probability that this path is not hit by any trajectories in 0 epsilon is e to the minus epsilon, the capacity of this path. So of course here, I didn't explain why we can factorize, but that's not very hard to prove. So, okay, so what we obtain is that the probability of that we're interested in is at least this. And so what remains to understand is this expectation here. So in order to understand this expectation, we need to understand the capacity of the first 10 steps of the loop erasure. So now let me just say that in expectation, and I will explain this in the next slides, the expectation of the capacity is up to constants, n over log n to the 2/3. So if we were to replace here the capacity by its typical value, then we would have to take epsilon to be the inverse of this ratio so that we cancel this exponential, and then we would get exactly log n to a third divided by n. So that proves the lower bound. So now I'm just going to explain why the capacity of the first 10 steps of the loop erasure is asymptotic to this. And of course, this is not enough because here we need to understand upper tail estimates, but this is actually not very hard to do. Okay, so let's go back to the capacity of K. The capacity of K is the sum, as we said before, of the probabilities that we escape K forever. And an equivalent definition is that the capacity of K is the limit as x goes to infinity of the probability that we hit K starting from x divided by the green kernel at x. So what we see is that in order to understand the capacity of a set, so here the capacity of the first 10 steps of the loop erasure, we need to understand intersection probabilities between loop erased random walks and simple random walks. So now let's take a step back and take two independent simple random walks in Z4 that start at distance root n apart. Then what Lawler proved is that the probability that they intersect when you run x up to time n and y up to infinity is up to constants 1 over log n. So let me give a wrong argument where this 1 over log n comes from. So if we write I for the total number of intersections, so here we want the path of x and the path of y to intersect, which means that they could meet but at different times. So let's call I the total number of intersections. So the probability we're interested in is the probability that the total number of intersections is positive, which is the expected number of intersections divided by the expected number given that this expected number is positive. This is a trivial equality. Now, if we start two walks at distance root n apart, then it's not hard to show that the expected number of intersections when you run one up to time n and the other one to infinity is of order 1. Now, what is the expected number of intersections given that you have one? Then you can, given that you have an intersection, you can think of having the two walks start from the same point And so then the total number of intersections grows like log n, just by the local CLT, as I mentioned earlier. So that's how we get the 1 over log n. But as I said, this is a wrong argument because there is no Markovian way of defining the first intersection point. Because in any way you define it, you will have information about the future of the path. So it's not going to continue as a simple random walk anymore. But Lawler proved this estimate here by conditioning on one of the two walks and looking at the expected number of intersections conditional on one walk and showing concentration results. Okay, so this is for two independent simple random walks. And now we can immediately get that the expectation of the capacity grows like n over log n. So here we take the capacity of the first n steps of a simple random walk. And now a very useful result due to Lyons, Pence, and Schramm states that if x and y are transient Markov chains, then the probability that they intersect is up to constants the same as the probability that the loop erasure of x intersects y. So of course, this direction is obvious. So what is remarkable is that they were also able to prove the other direction. So there is a universal constant, I think it's like 1 over 256 or something, so that these two probabilities are always related. So of course here it's for independent. Okay. So now what this means is that if we look at the capacity of the loop erasure of the first n steps of the random walk, this is going to be the same as the capacity of the simple random walk. And we know that this is n over log n, as I wrote in the previous slide. Now, using the result of Lawler that I mentioned earlier, we need n times log n to third steps of simple random walk in order to get n steps of the loop erased walk. And so the expectation of the capacity of the first n steps of the loop erasure is going to be up to constants the expectation of the capacity of the loop erasure of x of 0 n log n to a third. And now from here, this is the same as if we get rid of the loop erasure. So it's up to constants the same as the capacity of just the simple random walk up until this time. And so substituting here this value of n, we get what I showed earlier, the n over log n to the 2/3. So I just want to show you where these exponents come from. And this is the proof of the lower bound that I already explained before. So this is an almost complete proof modulo proving some upper tail estimates and some and also the independence that I wrote here. So the upper bound is much more delicate. And the way we obtain the upper bound is by considering Q of n to be the probability that the path contains a path of length n. And we prove an inductive inequality of this form. So Q of 2n is upper bounded by what we want to get plus Q of n multiplied by a quarter. And the importance of a quarter here is that it's strictly less than half. So then if you iterate this, then you get exactly that Q of n. So iterating, you get that Q of n is in fact upper bounded by log n to a third divided by n, which is what we wanted. And in order to obtain this, we had to understand the capacity of the loop erased. So we had to understand the capacity of the loop erased random walk and to prove concentration estimates. And to do this, we used some tools that were developed earlier with Amina Sela and Bruno Shapira, where we looked at the capacity of the range just of a simple random walk. And I'll stop here. This is just a statement of the theorem that I mentioned, that I stated earlier. Thank you.
Thank you, Perla, for a fascinating talk and some lovely results. So let's open it up to questions. So please, people, feel free to unmute yourselves and ask questions. Maybe I could ask something. So what happens in, so you've got the behavior in 4 dimensions is quite like behavior in higher dimensions, except you have these logarithmic factors difference. What happens in 2 and 3 dimensions?
So in 2 dimensions, everything is understood via SLE.
Mm-hmm.
But in 3 dimensions, this is the next project that we're doing. I mean, we have discussed, but we haven't finished yet. So in 3 dimensions, the exponent depends on the dimension of the loop-based random walk. So if you run a loop-based random walk in 3 dimensions and you wait until it hits the ball of radius n, and you want to know how long it took until it reached, then there is an exponent, and very little is known about this exponent. So what we get is in terms of this exponent. This is an exponent, I think it's called theta. It's the loop erasure exponent in 3 dimensions. So everything we get is a function of this exponent, but otherwise it's explicit.
And do you expect, broadly speaking, these types of polynomial behaviors?
Yeah, so you have polynomial behavior, but the polynomial depends on this exponent theta.
I see. Again, I had one slightly vague question, which is, so in more than 4 dimensions, you don't get the uniform spanning tree anymore, you get the uniform spanning forest.
Right.
Is there a sensible way of getting a uniform spanning tree in more than 4 dimensions, or is there some property that you have to lose?
You mean so that it is connected?
Yep.
So you mean if you can connect the different trees together?
Yeah, or have some slightly different generation process. So I guess I'm saying, is there some fundamental obstacle to having a uniform spanning tree with whatever nice
So there is a fundamental
translation
obstacle
properties
using these algorithms because of transients.
Mm-hmm.
But yeah, I'm not sure. I think that's a nice question. I'm not sure.
I mean, in principle, it might mess up local limits in some way that you wouldn't like, but.
So the natural thing is, you define your exhaustion and you take the limit of the uniform spanning tree on the finite graphs, and this converges to the forest.
Right, but you're sort of somehow conditioning on something happening.
Right. Yeah, I'm not sure.
Christina has a question as well.
I think I actually have 2 questions, but thank you for a lovely talk, Perla. That was great. For your middle results, where you've got the little o of 1 up in the exponent of the, so you've got a log n to the 2/3
yeah, right.
of 1. Is that sort of, so you said that for the lower bound you don't have the little o of 1.
Yeah, it shouldn't be there.
It shouldn't be there.
Yeah, it just, we couldn't get rid of it with our proof, but it just a technicality.
Right. And I suppose there are now scaling limit results in 3 dimensions. Is there a hope to get a scaling limit in 4 also?
Yeah, okay, that's a good question. So this is something that Tom is working on with Sarai Hernandez-Torres, who has been involved in the 3-dimensional one.
Yes.
Yeah, so it's working.
That's optimistic.
Say that again.
That sounds optimistic.
Yes.
Great. Thank you very much.
Anyone else like to ask a question? Okay, so maybe let me say thank you to Perla again for a fantastic talk, and let me invite everyone to break out and unmute yourself.